Okay, let's start. Hello, welcome to Math 3220, Foundations of Analysis 2. So this is basically a proof-based multivariable calculus class. Before we go on, I'm going to be recording the lectures. But you will be made anonymous. So I typically sort of take a week's worth of classes and I sort of put them together into one video and then put them online on YouTube. In the past, I've had good experiences with this. I think it was useful to students and me as well, to be honest, because I forget the things that I teach. But so that's that. So today I'd like to go over the syllabus, and maybe if you have time, we can start talking a little bit about math. Before I go on, are there any questions for me? Okay, so I'm not going to distribute the physical copy of the syllabus. It's on Canvas. So everything will be on Canvas. So my name is Alp. Here. I'm a postdoc at the math department, my third year and final year probably. And this is my email, my last name, uzman@math.edu.utah.edu. We meet on Mondays, Tuesdays, Wednesdays, and Fridays from 9:40 to 10:30, which coincidentally was the same times we met last semester when I was teaching the first class, the 3210. Office hours, in my experience, by appointment works the best. So that means that you're going to have to take some initiative to set up some appointments if you have any thing that you want to discuss. And our coordinator for 3210 and 20 is Professor Milicic. So if you have any issues that you feel like you won't be able to solve with me, that means that you're going to have to, you don't have to, but you have the option to reach out to Dragan. Course description. Math 3220 is a rigorous course in multivariable calculus, serving as a transition course from calculus to analysis. As outlined in the general catalog, it is worth 4 credits and has the following prerequisites. So you need to have taken 3210 single variable calculus version of this, and either differential equations or linear algebra. Just have a check. How many of you have taken differential equations? Okay, how many of you have taken linear algebra? Okay, good. It's kind of interesting because somehow in this class, the way we're going to use linear algebra, and we will be using a lot of linear algebra, is closer to how you use it in differential equations. But at the same time, you're going to need to have some sort of interface that is deeper, that you develop not necessarily in differential equations typically, but often in 2270. Okay, much like its prequel, Math 3210, Math 3220 is a proof-based class, and the emphasis will be on developing mathematical maturity. Okay, so if you look at the digital version of this document, you're going to see that this phrase, mathematical maturity, is in red. It's in a different color if you're colorblind. Hopefully you'll be able to see it, but if not, just let me know, and I'll make the necessary adjustments. In any event, all of these sort of highlighted or fonts that are of a different color, they are all hyperlinks, okay? So if you click on that, it's going to take you to an article that Terence Tao wrote back in the day, describing what mathematical maturity is. In particular, on rigorous argumentation, rather than calculation of the values of certain limits, integrals, or derivatives. We'll start with a review of linear algebra and an introduction to matrix spaces. So these are the sort of basic structures that we're going to need to use in this class. I will spend some time later today, I think, discussing the tentative schedule. Then we'll discuss differential and integral calculus of multivariable vector-valued functions. Finally, we'll bring together differential and integral calculi through the formalism of differential forms. So something like the Stokes theorem you should think of. And so just to give you an idea, in 3210, the types of functions that we're interested in are single variable and scalar valued, right? Now here, we're going to look at multivariable versions of this. So if you've taken the, I mean, you probably did, but when you're taking the multivariable calculus sort of standard sequence, what you typically do is, first you sort of turn this into a vector, right? These are like curves in space. Then you fix the output to be one-dimensional, turn the input to be multivariable. So these are like height functions, whatever. And if time permits, what you do is you look at vector-to-vector functions, okay? Imagine something like a vector field, right? So in three-dimensional space, you want to describe some sort of velocity information. This is how you do. And somehow it turns out to be the case that this is sort of the thing that you need the most. Of course, people look at even more complicated things. So maybe I should ask you, what is sort of like the next step? You have the scalar, one-dimensional thing. You have sort of like multi-dimensional vectors. And then what comes after that? Any guesses?
Really multi-dimensional matrices.
Yes, matrices, but more generally.
I believe the term is tensors.
Yeah, there are tensors. So you can imagine something like this. Etc. Okay. So somehow, for instance, it turns out to be a good thing to be able to think of matrix multiplication itself as a linear algebraic operation. That's where this tensor formalism comes into play. We're not going to spend too much time on this tensor formalism, even though I do want to sort of at least include some problems and stuff. Fundamentally, the reason why is because, at least in abstract, what you can do is you can what is called flatten. You can, for instance, this is like a, what is this? 1, 2, 3, 4, 5, 5 by 2 matrix. What you can say is that, oh, this matrix is basically a 10-dimensional vector. So that's like a flattening. And so you can just turn this situation into this, at least in abstract. Now, when it comes to more practical situations, it still becomes important to be able to think of tensor operations the way they are. But we'll get to that. This is, even though a lot of people here are applied math majors, the text seems to be more focused on sort of like this pure perspective. And I too am coming to this from a pure math perspective. Still, we'll see. We'll see. I have certain priorities, but if time permits, I would like to sort of include some stuff from there as well. Okay. Expectations. As a student, you are expected to attend all lectures 4 times a week, complete 12 problem sets, take 2 in-class midterm exams, and take a final exam. According to the university regulations, you should expect a workload of approximately 8 to 12 hours per week outside of lecture hours. That's a big time commitment. You will have some familiarity with many ideas and notions we will discuss throughout the semester. However, the focus on rigor can be hard to get accustomed to. Hopefully you started getting accustomed to sort of like proofs and stuff like that in the previous class, but it takes time. Missing lectures and assignments can make it challenging to catch up. Please stay engaged and reach out if you encounter any disruptions. We're here to help, but your hard work and dedication will be essential to getting back on track. Now, you've all taken 3210. It was a hard class. This is going to be even harder. Okay, I'm letting you know. I just imagine it's like the complications that were in this situation, whatever. This, it's like, and somehow it's not like linear multiplication. It's like, this is not like, what is it, 5 times harder than that. It's not, this case is not like 20 times harder than that. It's more like 50 times harder, in my estimation. So it's going to be a hard class. I mean, when I was designing the class, I was like, oh, I don't know how we're going to do this, but we'll see. Learning objectives. Among the objectives of math in math 30-20 are that you learn how to ambiguate and disambiguate vectors, matrices, and linear transformations. Okay, so this is like a subtlety that we're going to discuss this week and next week. If you take 2270, the linear algebra class here, they tell you, okay, so you have vectors, these are basically tuples of numbers, but if I were to write them as a tuple, this is the same thing as writing it like this. Right, that's what they say. Now, this is sort of, in a sense, it's true, and we're going to sort of do this identification at some point. But in reality, that is not the case. And we're going to have to sort of discuss how it is that this formalism is the same thing as this formalism, or under what conditions. Underneath this equality really is some sense of relativity. It depends on what is called a basis. You choose a basis for your space. In this case, this identification really uses what we would say the standard basis. There's a standard basis in R3 given by the XYZ vectors or IJK vectors in calculus language. But the point is that even though we're calling this the standard basis, there is nothing standard about it, mathematically speaking. Okay? So we're going to discuss all that. Apply vector and operator norms in proofs and computations. Leverage the triangular inequality in metric spaces to derive key results. Use level and sublevel sets of metrics to describe subsets of metric spaces. Use the foundational topological and uniform properties. Don't worry about these phrases if you're not familiar. We're going to get to all of this. Properties of metric spaces, including compactness and completeness. Prove and apply the Banach contraction principle. Prove and use the foundational theorems governing continuous functions, including the maximum principle and intermediate value theorem in the context of metric spaces. Now, as I'm reading this, and some of you in the audience have taken 3210 last semester from me, you're going to realize that I'm basically teaching this class. I designed this class so that we're basically following what we did in 3210. It's like some foundational stuff, differentiation, integration, fundamental theorem of calculus. That's sort of like my main idea, but it's more complicated in this situation. There are like multiple ways to differentiate and so on. Paradoxically, integrating is not that hard as opposed to single variable. Like Riemann integration, okay, partitions, whatever, it was hard. I'm just going to sort of refer to stuff that you learned in this class. Define and use derivatives and partial derivatives of multivariable vector-valued functions. Prove and use the foundational theorems governing differentiable functions, including the chain rule, mean value theorem, Taylor approximation, inverse function theorem, implicit function theorem, and rank theorem. Yeah, so the Taylor approximation and the inverse function theorem, you probably have seen these in 3210 as well, right? You haven't? Some of you know, okay. Taylor approximation is this, you take a function that you can differentiate many times, and you get to approximate it using a certain polynomial. And in certain senses, that polynomial, which is called a Taylor polynomial, turns out to be the sort of unique one. Let me perhaps remind you. This is a single variable case. F of x plus h equals f of x plus f prime of x times h plus f double prime of x divided by 2 h squared plus f triple prime of x, third derivative, divided by 6, h cubed plus higher order terms. Depending on how many derivatives you have available for the function, you can sort of keep getting higher order terms. That's data approximation. Inverse function theorem was telling you that something like this, if this is my function f, you see this, I cannot really invert it, right? Because it doesn't satisfy, what is this, the horizontal line test. But I can do it locally. So for instance here, the derivative, the slope of this tangent line, is not 0, right? It's not a critical point of f, which means that this is supposed to be sort of the relational inverse. At least near this point, f admits a local inverse, and really, near this point, it's a local diffeomorphism. That was the content of inverse function theorem. In single variable calculus, it's not that hard because somehow differentiable functions are already continuous, and we define functions on the interval, and we know that the images of intervals under continuous functions are intervals. So basically, the graph of the function is already in a square, in a rectangle. So that makes things rather simple in 3210. In 3220, we're going to have to work a lot, I would say, to establish this. And in fact, I would say that this is one of those big things that I hope you're going to get in this class, inverse function theorem. Implicit function theorem and the rank theorem, they're sort of related ideas. Okay. Maybe I should ask you too. You see, in single variable calculus, we know what nice sets are, right? Nice sets are intervals. Let me write it here. Maybe open-ended, closed-ended, whatever, but these are the simple situations. In multivariable calculus, there are a couple different sort of options. You could say, or maybe rectangles. And when we start talking about Riemann integration in multivariable calculus, we're going to sort of look at rectangles like this. But maybe a disk like this is a better option for sort of like the standard shape, because its boundary is nicer, right? It doesn't have sort of kinks. So its boundary is smooth, is what we would say. So it becomes more complicated, even to define what nice sets are in multivariable situation. Okay. Use critical points and extrema to describe and understand abstract landscapes. So things like Lagrange multipliers and stuff like that. So given a certain constraint, given a certain objective function, how do you figure out what is the optimal, or at which values, at which inputs, the function that you're trying to optimize gets optimized, for instance. Define Riemann integrability of multivariable vector-valued functions. Define and use Jordan measurability and content. This Jordan measurability is really about figuring out what it means for a set to be nice, so that you can do calculus. I'm not sure how much we're going to get into that, because, well, I'll say more when we get there. Prove and apply foundational theorems governing Riemann integrable functions, including Fubini's theorem and the change of variables formula. Okay, the change of variables formula you've seen in single variable as well. Okay, so let's say I have one interval I, another interval j, and I have a function taking real values. Right, so this is the so-called U substitution. Let's say that I have a diffeomorphism, a differentiable function from I to j, whose inverse exists and is also differentiable. That's what I call a diffeomorphism. That's what everyone calls it, diffeomorphism. And so you want to relate the integral of f over this to the integral of the composition, right? And so what should I put on the right-hand side? The integral of f over this domain should be the integral of composition, right? So f composed with phi, but I need a correction factor. This is this phi prime in absolute value. So, right, so when you do u substitution in single variable integrals, you need to sort of compute the du relative to dx, and you're going to have to differentiate. You're going to have to put that the derivative into the integral, otherwise the integral is not going to be the same, right? And the same thing holds in multivariable as well, but you're going to have to understand in a more foundational manner, let's say, what this is. So somehow this phi prime in absolute value tells you the infinitesimal distortion of the length elements in single variable. In multivariable, again, you need some sort of a number here, but this phi is going to be from a box to another box. So from a rectangle to another rectangle. We're going to figure out what it means to take the derivative of a phi from a rectangle to a rectangle. And then we're going to learn how to turn that derivative, multivariable derivative, into one number. Any guesses what that number can be?
It sounds like it would be a determinant.
Yeah, it's going to be a determinant, exactly. And so we're going to take a lot of these ideas from linear algebra and reinterpret them in the context of calculus. We're going to see, oh, determinant is not this number that you end up computing from a matrix. I mean, it is, but it's also sort of the distortion of volume. And you know, if you're not super comfortable with linear algebra too, I hope this class is going to be a good opportunity for you to rethink a lot of things, because I didn't like linear algebra as well. I didn't understand why people were interested in this, but I like calculus, and somehow seeing things in the context of calculus made a lot more sense for me, at least. Another thing that I didn't write here, but I want to discuss, is this idea of differentiating under the integral sign. So let's say that you have a function that depends on two things, and you're integrating, let's say, 0 to 1, some function f of x comma t. Okay? So this is like a position, this is like a time. So this is like a density on your rod that you parameterize to be from 0 to 1. But your density changes in time. And once you integrate relative to x, now this expression is still a function, but it's not a function of x, it's a function of t. So I can differentiate it relative to t. Okay, so how does the total mass change as the density changes in time? That's sort of like an idea. And of course, if you have this, you would like to be able to put this inside. But now you know, since you've taken 3210, that differentiation is one limiting procedure. Integration is yet another, more complicated perhaps, limiting procedure. And so taking this symbol inside really corresponds to changing the orders of the limits that you're taking. And you know that this is not always the case. You can't always do this. Of course, in engineering and stuff, you would like to be able to do this. And in many cases, in many situations where it does matter, you get to do it. But you have to work for that. And of course, what if I were to say that the endpoints of the rod 2 changes in time. Maybe the rod sort of expands and contracts and stuff. Now differentiating this is even more complicated, you see. But if time permits, I would like to discuss all this. And finally, prove and use multivariable analogs of the fundamental theorem of calculus from single variable calculus via the formalism of differential forms. Or before that, define and use vector fields in differential forms. So vector fields, perhaps some of you remember from multivariable calculus, the standard sequence, it encodes somehow directionality and magnitude. It tells you sort of motion. Differential forms somehow are the duals. If vectors are about, or vector fields are about velocities, differential forms are like speedometers, okay? Sort of detect velocities. So we're gonna have to discuss all this. And instead of sort of going through all of these different varieties of fundamental theorems of calculus and multivariable, so fundamental theorem of line integrals, Gauss theorem, divergence theorem, Stokes theorem, whatever, it turns out that there's a formalism called differential forms, formalism of differential forms. It's almost 100 years old now. That sort of incorporates all of this, curl, divergence, whatever, all of the formulas, and sort of compresses everything into one big algebraic formalism. So we're gonna have to spend a lot of time sort of discussing all that. But let me not say anything further about this for now. Okay, any questions so far? Okay. I know I'm sort of like all over the place today because I'm sort of trying to give you a sense, because I would expect that some of you are still sort of thinking whether or not you want to take this class. I'm going to sort of give you an idea as to what we're going to talk about. Tentative schedule, I'm not going to read this in detail. Basically, the idea is this. 2 weeks linear spaces, vector spaces, 2 weeks metric spaces. So these are two different structures. Then 4 weeks of differential calculus. We're going to have to discuss all of these different notions of differentiation in higher variable. Then 2 weeks of integral calculus. How do you integrate whatever? It's pretty much the same as single variable, to be honest. Modulo this Jordan stuff. Then we're going to spend 5 weeks on differential forms. Because it takes some time to get used to this formalism. So we're going to take our time because I want you to really understand these differential form stuff. Okay. Grades. So 5% attendance. Randomly, I will be taking attendance. 30% problem sets. Each week there's going to be one. 2 midterms, each 20%, final 25%. And then the grades are, they start at 90%. So if you get 90 or above, you get an A. And then every other is minus 5%. So A minus is 85 and so on. Textbook is the one by Taylor. We're just going to read the second part of the class, part of the textbook. And I've listed some supplementary material as well. Lectures by Terence Tao, Ali Ulgar, the professor who I learned this stuff from, at least part of it. And I really like this multivariable calculus notes by Paul Dawkins. It's like it's for the computational multivariable, but I still find it very useful because we're gonna treat things from a rigorous point of view, and sometimes you can just it's good to look at simple examples to keep your head to figure out what you're actually trying to do and stuff. Okay, and that's that. So I've taught 2700, I guess. Yeah, 2700 linear algebra 2 years ago, last year, sorry, in spring 2024, and 3210 last semester. And I was recording them like I'm doing now. And they're on YouTube, they're annotated and stuff like that. So, and throughout this class, I'm going to be referring to certain parts. of those lectures. After all, they are prerequisites. Part of why I'm doing that is that obviously I cannot assume that you've taken these classes from me, but at the same time, these classes, their content, it depends strongly on from whom you took these classes. So the style is different, even the content is different sometimes. And so this is like a partial remedy, perhaps. Hopefully it will be helpful. Okay, lectures. Attendance at all lectures is expected. Attendance at random lectures will be taken and will have an effect on the final grades. The number of lectures when attendance will be taken will also be random. A certain number of recorded attendance days may be dropped at the end of the semester. On weeks when a midterm is scheduled, now all of these are on Canvas, by the way, i.e. weeks 4 and 10, first two classes will focus on topics as usual, whereas the class before the midterm is reserved for review. So we're going to do regular class on Monday and Tuesday. Wednesday is going to be a review. Friday is going to be the midterm. Okay, and whenever we have a midterm, you're not going to have a problem set due that day. Okay, so each week you're going to have only one boss, either a problem set or an exam. I like to keep things simple. I mean, it's already complicated at this point. So, likewise, the last class on the last week, i.e. week 15, will be reserved for review. Lecture recordings, video recordings of lectures, excluding those reserved for reviews and midterms, will be uploaded weekly to the following YouTube playlist. So you can click on that and it takes you there. Problem sets, let me skip this because I haven't distributed even the first problem sets yet. So it's going to be up on this Friday, and I think on Friday's class I would like to say a couple of words about problem sets and stuff. Okay, that's fine. 2 midterm exams. During the midterm exams, the use of external resources will not be permitted. Your exams will be digitized and uploaded to Gradescope by the staff. You will have access to view how your exams are graded. Same thing with the final exam. There's a math center. There are tutors there that specialize in 3220. I would highly recommend you go there and seek help. This class is definitely one of those where you want to get all the help you can. Accessibility. The University of Utah seeks to provide equal access to its programs, services, and activities for people with disabilities. If you will need accommodations in this class, reasonable prior notice needs to be given to the Center for Disability and Access. The address and phone number is there. CDA will work with you and the staff, meaning me, to make arrangements for accommodations. All written information in this course can be made available in an alternative format with prior notification to the Center for Disability and Access. Inclusivity and safety. Title IX makes it clear that violence and harassment based on sex and gender, which includes sexual orientation and gender identity/expression, is a civil rights offense subject to the same kinds of accountability and the same kinds of support applied to offenses against other protected categories such as race, national origin, color, religion, age, status as a person with a disability, veteran status, or genetic information. If you or someone you know has been harassed or assaulted, you are encouraged to report it to the Title IX coordinator or the Office of the Dean of Students. Addresses and phone numbers are there on the document. For support and confidential consultation, contact the Center for Campus Wellness. To report to the police, contact the campus security, and there's also SafeU. There's this debate as to whether or not one should read the syllabus the first day, especially these parts, but I think overall it's good to sort of get this out of the way and spend enough time and then focus on the math afterwards. So, academic honesty. Okay. You are expected to adhere to University of Utah policies regarding academic honesty. This means that ultimately all work you submit must be your own, created without unauthorized assistance, and all external resources, including generative tools and computer algebra systems, must be properly cited and documented within your submissions. Any student who engages in academic dishonesty or who violates the professional and ethical standards may be subject to academic sanctions as per the University of Utah's Student Code. Generative AI and computer algebra systems. In this course, you may use generative tools like ChatGPT or DeepSeek, whatever, Claude, as well as computer algebra systems such as MATLAB under specific guidelines. These tools are permitted to guide your understanding of problem sets and topics. When using them, you must submit logs of your interactions as part of your problem set submissions. We're going to discuss more how any of this works this Friday. These tools can also be used to verify calculations, but remember, computations are generally expected to be done manually unless explicitly stated otherwise. You are responsible for ensuring the validity, accuracy, and relevance of your submissions, whether or not you use these tools. While encouraged, the use of such technology is not required for success in this class. The policy governing the use of such technology is specific to this class and section. Other courses and sections may be different, may have different policies. So my general idea is this, okay? So I designed this class so that it's sort of useful to as many people as possible. Some of you are going to go to grad school. Some of you are going to sort of, maybe in math and maybe in other areas. Some of you are going to sort of do something else. But ultimately, this is about mathematical maturity, ultimately. And no matter what you do, eventually, hopefully, if you end up encountering or interfacing with other mathematicians, at least this class is going to give you some idea as to the type of training they go through. And so you're going to have to, you're going to be available, hang on. You're going to be able to talk to them in a language they would understand, perhaps. So you're going to learn a little bit how they speak and how they think. And regarding AI, it's an arms race right now, in education as well. And so my idea is that if you can just use AI to handle your proofs and stuff like that, whatever you end up learning is not going to be something that you're going to be able to use later in your career, because AI is going to be able to do it for you. And so, yeah, we'll see how that goes. Hopefully, we'll be able to sort of find a middle ground, to say the least. But generally speaking, I am not against the use of AI. Have at it, but yeah, I mean, you should be working on things also. So we'll see. Regret clause: if you commit an unreasonable act but bring it to the staff's attention within 48 hours of the relevant submission, sanctions may be limited to that submission only, rather than leading to further disciplinary action. This clause will not be applied in the case of repeated violations. Okay, and that's it. So any questions? I guess one concern I have regarding AI is that as time goes by, it may even become impossible to determine whether or not you used AI, right? Because they're sort of incorporating all of these systems into whatever you're sort of using. And so we're going to have to sort of figure out as time goes by. Any questions, comments?
Question?
Yes.
Is there going to be a digital version of the textbook, or are we just supposed to source like a physical copy?
I mean, I think you're supposed to buy a physical copy.
Yeah, I just know there's like instant access through the campus store. I didn't know if you wanted to use that.
Oh, no, I mean, it's up to you. Like, I don't know.
I just know you can't can't do it unless the professor posts it.
Oh, really?
Yeah, but figure it out.
No, yeah, so it's good. Can you send me an email? I would need to ask Dragan about this.
Yeah.
So, I don't know. That's a good point. I mean, just search the title of the textbook on DuckDuckGo and see if you can find a PDF somewhere. Wink, wink. Okay. One final thing. Some of you have taken the previous class from me. If you're comfortable, could you raise your hand so that people around you can see? So you have some sense as to what type of a person I am and what type of a teacher I am. But if you want to sort of get other, other opinions from the other side of the aisle, let's say, I think it would be good to ask your colleagues about this. Okay, so do we have any other things to ask about or talk? Well, I guess I should say one thing. I will not be following the textbook line by line. And so if you look at the tentative schedule on the syllabus, I have topics for each week. And I also list, for instance, here, this is for week 1. It says week of August 18, today. It says linear spaces 1. Because the next week is going to be linear spaces 2. And then there's this part in parentheses. I'm telling you which sections these correspond to, approximately. So it says 7.1, comma, 8.4, dash 5. Okay, so I'm sort of jumping around a little bit, it seems like, because the point here is that in the textbook, they just describe Rn, so the space of all of these vectors if you want, but they don't do much with them. They don't say anything about linear transformations, whatever. You talk about other things, and then right before we're going to start talking about differentiation, they say, oh, by the way, there's this thing called the linear transformation, there's something called the basis, whatever, blah, blah, blah. To me, that didn't make that much sense. I'd rather sort of talk about linear algebra, be done with it, and sort of keep repeating these same ideas. So that's sort of why. Another thing, for instance, is that the theorems I'm going to state, they're going to be in the textbook, but maybe they're going to be phrased differently. So a big part of your job is going to be to read the textbook, get confused about what that corresponds to in the class, maybe ask me, or think about sort of how that theorem or theorem 7.5, whatever, in the textbook corresponds to this theorem that I mentioned. Another thing I'm going to do perhaps is sort of lump a bunch of theorems together and stuff. So it's going to be your job to compare and contrast the resources. Okay. So this is not a sort of low-level class. And mathematical maturity is sort of, part of it is this. Part of it is improving your literacy in math. Part of it is being able to sort of figure out how this idea gets transformed in this other person's mind and whatever. Okay. So let's start with some stuff, because we have, I think, 5 minutes. Linear spaces. Now, I'm not going to spend a lot of time defining a vector space. You're going to see throughout this class, even though this is a proof-based class, I'm really interested in taking something, differentiating it, and setting that derivative to 0. Okay? So this vector space stuff, okay, it's important, the axioms and stuff. We have some familiarity, and that's going to be sufficient for us. So a vector space or a linear space is a triple phi, alpha, and sigma, where B is a set. Alpha is a function that takes two vectors, gives back one vector. And sigma takes a number and a vector, gives back another vector. Of course, this alpha is vector addition. Sigma is scalar multiplication. They have to satisfy certain axioms. I don't want to write them down. Okay? What is more important are examples. So from linear algebra, we know that Rn is a vector space. Right, so this is the set of tuples. Now in 3210, I spent a whole week discussing this notation. Since some of you, or many of you, most of you haven't taken 3210 from me, I think it would be a good idea to go through the symbols. So this is what is called a set builder notation, okay? These curly braces. You open brace, close brace, there's a bar in between that separates the left-hand side and the right-hand side. Left-hand side gives you the typical form of an element in this set. The tuple of numbers, n tuple. x1, x2, and so on. It's with parentheses, regular parentheses. That means that these are ordered, which means that if I were to change the order of any two of them, that would be a different element. Okay, so 1, 2 is not the same thing as 2, 1. This is to the left of the bar. To the right of the bar, I have xi. I is an index, and if I want to be a little bit more rigorous, I'm not going to do this throughout this class, but just for today, let's do it. I would write it like this. For any I, x sub I is in R. So this symbol, upside down A, stands for all, okay? It's one of these logical symbols. For any I, this symbol, it's an E, says element of. Okay? For any I element in this set, going from 1 to n, x sub I is an element in R. Okay, this is just like a formal way of saying that this is the set of n tuples of real numbers. How many of you have seen symbols like this before? Okay, almost all of you. Good. Because I know that in 3210 too, some people just skip this stuff. It's convenient. It allows you to compress a lot of things. Another important set that ends up being a vector space is a set of n by m matrices with real values. This is going to be my notation for that set, that space. With okay. Are we happy with calling this a vector space? I'm going to speed things up in the coming days, but since this is today, this is the first day, let's keep it simple, right? Because if I have two vectors, two matrices of the same dimensions, I can add them up entry by entry, and I can scalar multiply, of course. I can scale each entry by the same number. That's what it means to be a vector space. Okay, this is it for today. We're going to continue tomorrow. Thank you. Okay, let's start. Good morning. So we're going to keep working on linear spaces. So just to summarize some of the things that I discussed yesterday a little bit, I wanted to sort of make sure that we're on the same page. So this, I use this notation, V cross or V times V yesterday. Just wanted to make sure that we all understand what this means. This is an operation on sets. If you have two sets, or more actually, from these two sets you can come up with a new set, which is the Cartesian product of, in this case, x times y, or x and y. It's the set of all those pairs where the first entry, lowercase x, comes from the first guy, and then the second entry comes from the second one. Okay? So this is one of the many ways of coming up with new sets from old ones. And when I write something like this, f colon x to y with an arrow, that means that f is a function whose input space or set is x, output space is y. And if I use this barred arrow, that means that a typical element in the input space is x, and f is sending it to y. So that will be y equals f of x, if you want. Okay, vector space is a triple V, alpha, and sigma, where V is a set. It could be any set. What is important is these two operations. Alpha is supposed to be something that models vector addition, and sigma is something that is supposed to be modeling scalar multiplication. So that means that alpha is a function that takes two vectors and gives you back some other vector, and sigma takes a scalar and a vector and gives back another vector. And these are supposed to satisfy certain axioms so that what you know from linear algebra, all of that works. Okay? And of course, any sane person, instead of writing alpha and sigma, writes instead of alpha of v1 comma v2, v1 plus v2. With the understanding that this plus could be something abstract, right? And likewise, instead of writing sigma of c comma v, you want to be reasonable, you just write c times v, or cv, in short. Okay? Now, there's a place for thinking about vector spaces like this in abstract. So there are some people who sort of study these kind of things, but we're not going to worry too much about these kind of things. So any questions about this so far? Okay. What is more important than the definition of a vector space, which I sort of, which I'm leaving as sort of something like, vague in a sense. I'm assuming that you have some idea as to what vector spaces are. What is more important is the notion of a linear function or a linear transformation. And instead of thinking of linear transformations as matrices from the get-go, I want to think of it from a functional point of view. And so vector spaces are defined in terms of certain axioms, certain structures. Linearity of functions is defined in terms of the function respecting those structures also. So the sum of two vectors, f should take to the sum of the outputs. And likewise, a scalar multiple of a vector in the input should turn into a scalar multiple, the same scalar multiple of the corresponding output. Okay? Now, maybe I should mention this. If you want to be formal, you probably want to put some sort of logical quantifiers here. Maybe you want to say, after writing this, for any vectors v1 and v2 in capital V in the input space. And here you want to say for any number c and for any vector v in V. I want this to happen, right? But it's clear from context what the logical quantifiers should be in this case. Now, there are more complicated statements like continuity, uniform continuity, whatever, where the order of quantifiers even matter, right? So because you have for all their existence, stuff like that. But for now, I think this is fairly straightforward. So while part of this class is about, coming to terms with rigor, instead of thinking of rigor as something you have to always abide by, these rigorous sort of like rules, I would rather have you think about rigor as something of a spectrum. Depending on the situation, you want to be perhaps more rigorous or less rigorous. at the very least, it should be something within your control. Okay? And throughout this class too, you're going to see this. When under certain circumstances, I'm going to be more rigorous. I'm going to get more technical. I'm going to sort of write things more in detail. Sometimes I'm going to sort of wave hands a little bit more. And this is sort of more appropriate, I think, to how, more akin to how mathematicians actually do math. Okay, so whenever we have two vector spaces V and W, you can look at the set of all linear functions, linear transformations from V to W. And I'm going to denote this set by this, L of V comma W, or semicolon W. Okay. Examples of vector spaces, Rn. So using this notation, Rn really is a shorthand for R times R times R all the way, so n copies. In a class where you focus more on this abstract linear algebra stuff, you would spend more time on this statement. What is really happening here is something interesting, because what you're doing is you have this R, which you are familiar with. It's this totally ordered field that contains the rational numbers, which in and of itself is a vector space. Addition is regular addition. Scalar multiplication is just regular multiplication. These are one-dimensional vectors if you want. And you get, as a set, you can take its Cartesian product with itself, but somehow this immediately inherits the vector space structure, right? So you just add entry-wise, scalar multiply entry-wise. But we're not going to spend time on this. I think it's fairly clear that Rn is a vector space. Maybe I should mention also that when I'm defining this vector space, I really mean a vector space over the field R. There are other fields, rational numbers, complex numbers, p-adics, binary, whatever. But we're not going to deal with those. So I just want to keep it simple. My scalars are always going to be reals. Okay. The next example is the space of n by m matrices with real values. Of course, if I have two matrices with the same dimensions, I can add them entry-wise, scalar multiply one matrix by the same number. These are valid things. So this is a vector space. The set of all linear transformations between two vector spaces itself is a vector space. This is where things start to get complicated a little bit, because somehow linear transformations themselves can be thought of as vectors, right? Because what is a vector after all? It's an element in a vector space. If I have any set x, and I can look at the set of all functions, this is my notation for the set of all functions from this to this. The set of all functions from a set into a vector space is a vector space itself. We just add entry-wise. So these are really examples coming from linear algebra. And these, I'm going to mention what these mean, come from calculus. This next example is my notation for the set of continuous functions from the closed interval 0, 1, taking real values. Okay, because if I have two continuous functions, I can add them up. The sum is also continuous, right? You probably proved this in 3210. And of course, if I were to take a scalar multiple of a function, continuous function, that is going to result in a continuous function. I can in fact do more, right? If I can take, so I can take two continuous functions and multiply them too. But vector space, that is not a vector space, that is not a linear operation. In a sense, it is linear, it's a bilinear operation, but that function multiplication is not part of the vector space structure. So it's an additional structure. The next one is a space of continuously differentiable functions taking real values defined on the open interval from 0 to 1. So this is a new notation for some of you. Instead of using this, I'm just going to use this, okay? So this is sort of like a more American or a more British way of writing things, and this is more Frenchy way of writing things. The idea here is that you want to think of intervals as Lego pieces, okay? So 1, 2, and so if this is a closed interval, right? So here in this set, let's say I'm including 1 and 2, I would use closed brackets. And so if I'm taking 1 here, I want to say that this is 0, 1, 1 not included. So instead of parentheses, I'm going to use these outward brackets. It looks kind of, cumbersome a little bit, but once you get used to it, I think you're going to see the value. Another point here is, of course, that when you see this out in the wild, you might sort of mistake it for a pair of numbers, a tuple, which is not quite the same, right? So that's that. And this one is the space of Riemann integrable functions. Again, probably you've studied this in 3210, because if I have two Riemann integrable functions defined on the same interval, I can add them up. And of course, the sum of the two Riemann integrable functions should be Riemann integrable, and so on. Right? And we're going to see many more examples throughout the class. Any questions about any of this so far? Okay, let's think about some examples of linear transformations. Perhaps the best example to start with is identifying linear transformations from R, that's a vector space, to R itself. So these were examples of vector spaces. Let me write it. Here. So this is a general rule in math. Whenever you define a structure, in this case a vector space structure, you want to immediately think about transformations that preserve that structure. In this case, linear transformations. And so here are examples of linear transformations. Linear functions. Let's say that I have a function, let's call it L to be more evocative. Let's say that this is linear. What can I say about this? Or can I sort of think of it in a simpler manner? Any guesses? Mm-hmm. Yes, but maybe something simpler I'm looking for. Yeah.
L of x equals 2 for all x. Like it's...
That's not quite a linear function, actually. It's a constant function.
It's affine. It's affine.
Yes, that's an affine function.
It equals 0.
Yeah. Yes, fair enough. But the point, I guess, the answer I was looking for was the following. Linear transformation, okay. I have some idea, but instead of a transformation, if I can think of just a number, I would prefer that. And indeed, in this case, perhaps surprisingly enough, this x, the input itself, is on the one hand a vector, but on the one hand is a scalar, which means that I can take it out. Right? So a linear function is completely determined by one number, namely where it sends the input 1. Okay? That is to say, linear functions between reals to reals, or from reals to reals, is nothing but multiplying by a number. Okay? And graphically, of course, what does this mean? It means that it's a line passing through the origin. Okay? And so based on this, maybe I can go back to the definition of differentiability in the context of single variable calculus, and I can say something like a function is differentiable, let's say at 0, at the origin, if there is, so this is my notation for, or abbreviation for the phrase there is. See, we had the backwards A, or upside down A, that was for all. That's one of the logical symbols. This is the other one. This is the backwards E, stands for there exists. If there's a linear L such that limit as h goes to 0 of f of h minus f of 0 plus L of h divided by h goes to 0. Okay, so of course now we know that this L of h is nothing but h multiplied by some number. That number is supposed to be f prime of 0. In single variable calculus, we just say it's a number. But now, you see, this is exactly where linear algebra is going to start sort of getting into the folds. Instead of saying the derivative of a function at a point is a number, we're going to say it's a linear transformation. That's all there is to it. It's going to take some time. We're going to have to develop some of these ideas. But that's where we're going. Okay? Any questions about this? This is one of the fundamental ideas of this course. So somehow we're going to say, oh, you know, in multivariable calculus, instead of numbers, we need sort of higher dimensional numbers. And the way you handle higher dimensional numbers is by linear algebra. That's the main idea. Questions, comments? Okay. More examples. Let's look at linear transformations from R2 to R2. You don't need to take the input and output to be the same space, but it's just perhaps it's somewhat more convenient, at least initially. So linear. Well, if that is the case, again, I want to simplify this L. Instead of thinking of it as a transformation, I want to sort of reduce it to a bunch of numbers, basically. Okay. I'm thinking about, oh, how many numbers do I need to determine or fix to specify what L is, right? In this case, all I needed to do was to specify this particular number. Once I fix that, I know the whole function, okay? In a sense, it's less complicated. And so what I can do is this. Now, first of all, my inputs are going to be vectors with 2 entries. Right? This is the space of tuples, or pairs. And the output is going to have 2 entries as well. So maybe I can call them A of x comma y, comma B of x comma y. Okay. I'll leave it to you to determine that in order for L to be linear, both A and B have to be linear. That's an exercise. And that means that I can do some stuff, right? So I can do something like this. X comma y is nothing but x times 1, 0, scalar multiple of a vector, plus vector addition, y times 0, 1. Let me be explicit here. Okay, because A is linear, I can distribute and then because this x is a scalar, I can take it outside, right? And likewise here, I can take y outside. And so again, the moment I determine what A of 1, 0 is, and A of 0, 1 is, what that is, I know what the A component is, and likewise, I would need 2 numbers for B. That means that in total, if I were to specify 4 numbers appropriately, that would determine my original transformation L. Of course, this is not something super crazy, because from 2270, I hope you expect that ultimately, modulo some math stuff, this L should be a 2 by 2 matrix, which means that it is determined by 4 numbers. Okay? The point here is that to figure that out, you don't need to think of linear transformations as matrices. And we haven't been doing that so far. Also note, I'm not using matrices at all. Any questions or comments here? The reason why I'm doing this is that, okay, in the context of finite dimensional stuff, that's fine, but when you start doing calculus, many things turn out to be, again, linear transformations, but not necessarily of matrix form. So what are examples of linear transformations that are perhaps more complicated than matrices? An integral, right? So that's a vector space. Okay, so that means that by definition, any vector here is a Riemann integrable function. That already is a complicated thing to think about, right? I have vectors, but each vector is a graph, in a sense. And Riemann integration takes the function, turns it into a number, but it does so in a linear manner. Right? So the integral of the sum of functions is the sum of the integrals. Okay, let's write it down. That's an important point. How to write this? Let's say I for integral goes from the space of Riemann integrable functions into reals, where you take as an input a function f, and I of f is supposed to be the integral from 0 to 1 of f. That's a linear transformation. Okay, you prove this in 3210. Okay. Of course, if integration is linear, certainly differentiation should be also linear. And in fact, what I can write is something like this. D that goes from once continuously differentiable functions defined on the open interval. But if I were to take a once continuously differentiable function and differentiate it once, I'm going to end up with a function that is 0 times continuously differentiable. That is to say, that's continuous. So when you apply the d operator, the derivative operator, you decrease the superscript by 1. Of course, C2, for instance, means twice continuously differentiable and so on. Take an f, send it to f prime. That's a linear transformation. Okay? If I were to take two functions that are differentiable, take their derivative, take the derivative of the sum, that's going to be the same thing as the sum of the derivatives. And of course, a scalar multiple of a function, if I were to differentiate, I can take the derivative outside. That's what it means for differentiation to be a linear transformation. Okay? How about multiplication? D of fg is not the same thing as d of f times d of g, right? So you cannot just distribute differentiation. There's a product rule, Leibniz rule, whatever. But that's not a problem because, like I told you, function multiplication is not part of the structure of a vector space. Okay? There's a name for operations that satisfy this as well. These are called derivations, evocatively, but for the purposes of linear algebra, that's fine. What else? There are many more perhaps, but I think this much is enough. Okay. Any questions about any of this so far? Now, well, at the end of last semester, when I taught 3210, I was talking to someone who took the class, and he was talking about how, it was kind of confusing when I asked about whether or not people had any questions. He said, like, it's like, there's so much material here that, you just like do a bunch of things, you prove something, and then you ask, are there any questions? But like, I'm still trying to digest what is happening. That is true, but now that I told you this, perhaps what you can do is, as you're sort of listening to me, you can sort of keep note of your own questions, and maybe sort of the moment I ask, are there any questions? You can just, have at it. Because in a sense, in math, I'm sure some of you have had this experience. Sometimes you're confused, but even figuring out how to state what you're confused about is a problem, right? It's like, I'm confused about something, but I don't know how to say it. So I think that's going to help you sort of understand things a little bit better. Indeed, often it becomes important to be able to even ask what you're confused about in the right way somehow. Okay. Of course, you don't need to wait for me to prompt you to let me know if you have any questions. You can go ahead at any time. That's like a specified situation. Yes?
Why did you say, so on that AXY, did you just assume AXY is linear to just write that out as a hint for how to do the problem set?
Assuming L is a linear transformation, it has to be of this form.
Yeah.
I'm saying if L is linear, A and B have to be linear also.
Mm-hmm. I just guess like that AXY part, you expanded that out. That's just, you assume AXY is linear.
Yes, exactly.
Okay, but you don't.
I mean, I'm not assuming. I'm saying here, if I need to be formal, I really need to verify that A is a linear transformation in order to do this.
Okay.
But I'm just leaving that to you.
Do something similar with L to show that.
No, not quite. So, okay. I'm saying from the beginning, let's say that L is a linear transformation from R2 to R2. I'm going to reduce L to a bunch of numbers. Okay? By definition, because L is from R2 to R2, it has to take something that has two inputs, and it has to have two outputs. Now, here, I'm saying, then I can show, only using the assumption that L is linear, that these two components have to be linear also. I was bluffing there. It is true, but I didn't do it. I left it to you. Okay? Now, using that, I can keep going.
Okay. Yeah.
Okay? Wait.
Sorry if
Yeah, yeah.
not done. Could you go over the construction of how that derivative statement is made to show it's differentiable as zero? I'm not sure how we got that.
Okay, if I were to say f from R to R is differentiable at 0 if there is a number denoted by f prime of 0 such that here f prime of 0 times h, instead of L of h I write this is equal to 0.
Okay.
This is the definition of differentiability at 0.
Oh, that's just from definition.
Yes.
Okay.
I just rewrote the definition using linear algebra.
Okay, so that's what this is showing.
Yes.
Okay.
So this is the same thing as this, yeah.
Okay, you're just showing that's equivalent to the other definition.
Yes,
All right, that's not too bad.
yeah. Of course, one thing that we're going to have to worry about a little bit is that, I mean, if you've taken 3210 from me, we did worry about this quite a bit. But in this case, you actually don't need to well, in either case, perhaps, you need to sort of think a little bit about this number being unique. It does turn out to be unique. In a sense, this is the unique affine function that is tangent to f at 0. Okay? So this is the best linear approximation to f at 0.
Cool, thank you.
Yeah, yeah. Any other questions? So the point I was trying to make here is that in 3220, what we're going to do is we're going to look at whatever we did in 3210, and whenever there was a number or a scalar function, we were going to say, okay, so using linear algebra, if my inputs are vectors, how can I still make sense of the same expression? Okay, so for instance, in higher dimension, this h is not going to be a number, which means that you cannot divide a vector by a vector. But in single variable too, I can just put absolute values here. That's still valid. In higher dimension, instead of saying that these bars are absolute values, we're going to say these are norms. We're just going to upgrade everything to a higher dimension. Okay, now this makes perfect sense. Even in higher dimension, actually. I mean, to the extent that if you want, I can already give you the definition of differentiability in higher dimension. From Rn to Rm is differentiable at 0, the 0 vector, if there's a linear transformation from Rn to Rm such that this happens. We don't know what this norm means in this case, but it's supposed to be the Euclidean norm, for instance. We're going to see that it actually doesn't matter. We're going to get to that in a month. So don't worry if this is kind of confusing. Any other questions? Okay. So one of your colleagues mentioned this phrase, affine function or affine transformation. It's very similar to linear, but it's not exactly the same. So let me just give you the definition. Now, instead of defining what it means for a function to be affine between what you would expect affine spaces, I'm just going to define what it means for a function to be affine between linear spaces. Because it turns out that defining an affine space in abstract is more cumbersome than linear spaces, so I'm just going to, bypass that. So definition. Be vector spaces. A function f from v to w is affine if there's a linear transformation, let's call it L, and a vector in the output space, let's call it W0. Such that for any input b, f of b equals L of b plus W0. So you first apply a linear transformation and then you translate it by a vector. Okay? And so for instance, constant functions are affine functions. Two more definitions, or maybe one more. There are many definitions actually. So let's also define this. It's going to be important. Linear subspace of a vector space. Well, it's just a subset that is closed under addition and scalar multiplication. Vector subspace let's say H of V is a subset of V that is closed under addition and scalar multiplication. Addition and scalar multiplication. So for instance, in three-dimensional space, I can think about a plane passing through the origin. That's a linear subspace, or a vector subspace. What is more important, perhaps, is the ideas, the notions of kernel and image. These are subspaces that you can associate to any linear transformation. In terms of 2270, we had nullspace and columnspace, but that's sort of using the language of matrices. In general, you use the words kernel and image. Let L be a linear transformation from V to W. Then ker of L, if it's supposed to be the null space, or the abstract null space, it should be the collection of all vectors in V that L sends to 0. V and capital V such that L of B equals 0. Is the kernel of L, and M of L is a set of all those outputs that is of the form L of V, right? So the column space is supposed to be the image. Is the image. So this is sort of another way of saying null space. This is the column space. And then this is the column space. So the kernel is supposed to be all those vectors in the input space that my transformation collapses to 0. And the image, or the image of a linear transformation is supposed to be all those possible outputs that I can obtain after applying L to whatever vector in the input space. Okay? I'm going to leave it to you to verify that indeed these two are vector subspaces using that definition. This is a very nice exercise. Is a subspace of V M is a subspace of W. Now note that even though I'm basically talking about null space and column space and stuff, I still haven't used matrices as linear transformations. Okay. Any questions or comments about any of these? I know that I'm just throwing at you a bunch of definitions. I think all of these is just like 2 paragraphs in the textbook. But I thought it would be good to just spend some time going through these ideas. Certainly, hopefully, at least some versions of these you've seen before. If this is the first time you're seeing ideas similar to these, maybe you may want to talk to me and see what we can do. Questions? Comments? Okay, so I told you that, okay, in math we have a bunch of structures, and then I told you that whenever we define a certain structure, you immediately should start thinking about transformations that preserve that structure. This is, vector spaces leads to linear transformation, for instance. But then you want to go one step further, and you want to talk about invertibility as well. Okay? So we're going to have a bunch of different notions of invertibility in this class. The first one is invertibility in the sense of linear algebra. That's what it's called, a linear isomorphism. In week 3, when we start talking about metric spaces, we're going to start talking about invertibility in the sense of continuity. That's what people mean when they use the word homeomorphism. And then once we start talking about differential calculus, in week 5, I think, we're going to start talking about immutability in the sense of, well, differentiable structures. That's what people mean when they use the phrase diffeomorphism. I've already used that word yesterday as well, and in 3210 I use it a lot of times, but since many of you haven't taken this class from me, I'm just going to go over all of these again. So here's the definition. Let V, W be vector spaces a linear isomorphism two different words, separate words, from V to W is a linear is an L is a linear transformation from V to W that has a functional inverse. So L minus 1, L to the minus 1 exists as a function, and that too is linear. A functional inverse and L to the minus 1 is a linear transformation from W to 1, W to V. In this case, I would call V and W isomorphic as vector spaces. And here's a very nice exercise. In fact, this last statement is redundant. If you have a linear transformation that has a functional inverse, that functional inverse has to be linear. So this part is automatic. It's a nice exercise. To give you one example, and this is going to be an important thing that we're going to discuss tomorrow as well, the so-called classification theorem for finite dimensional vector spaces. We still haven't talked about dimensions, so we're going to have to talk about that as well tomorrow. But in fact, the space of linear transformations from the reals to itself is isomorphic as a vector space to reals itself. Let me write that down. That's going to be an exercise. And that's going to be the symbol for linear isomorphism, or isomorphism in general. The linear space of linear transformations from the reals to itself is isomorphic as a linear space to the reals. Not as a field, but as a linear space. Okay, I think that's a good place to stop. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. So today, finally, I hope we're going to start talking about matrices as transformations. We need to talk about these gnarly subjects: linear independence and span, basis, whatever. So these are sort of like some of the ideas that you typically sort of spend plenty of time in 2270 to get accustomed to. These are sort of the abstract parts of 2270 in a sense. And then we're going to be able to talk about things like dimension and stuff. But before getting into that, I wanted to perhaps talk a little bit more about this exercise that I finished yesterday's class with. I told you that the space of linear transformations from reals to itself is isomorphic as a vector space to reals itself. So on the right-hand side, I'm thinking of R as a vector space. Scalars are vectors, albeit one-dimensional, so to speak. And so what was this idea of a linear isomorphism? That means that, okay, so this space has a vector space structure, this space has a vector space structure. For isomorphism, we're going to see later another method, but at least for finite dimensions. For isomorphism, the way we defined it yesterday was, if I have two vector spaces, I need to display one isomorphism, that is to say, one linear transformation that is invertible from here to there. So now I should ask you, do you have any guesses as to how one can come up with this linear transformation from this space to this space? So I want maybe a capital phi that goes from, let's say, the left-hand side to the right-hand side. I want this to be linear, and I want it to be invertible also. Any ideas?
Bit of a guess, but you mentioned the linear transformations are defined off one number, so could we just directly map that to the reals?
Yeah, for instance, if I were to take as an input one linear transformation, where do you want to send it?
Just exactly to whatever real value defines that transformation.
But what does that mean mathematically?
Yeah, the definition of L of x equals x times L of 1, just the L of 1 value.
Yeah, so,
That to the real on the right side.
okay, so you're saying that, so your colleague is suggesting that let's define this phi to be that transformation that takes a linear transformation, sends it to its value at 1. It's kind of a bizarre thing to do in a sense, because we're used to thinking of functions taking inputs to outputs, but in a sense, we're now thinking of inputs as acting on functions. It's kind of a bizarre thing, if you think about it. Take a function, evaluate it at 1. So geometrically, what does this mean? I know that any linear transformation, its graph should be a line passing through the origin. So you feed to this phi some line like this, some picture like this. What it does is, it looks at its height, the height at when x equals 1. You feed to this machine this picture. It gives you back this value, whatever that value is. That's the machine. And indeed, it turns out that this is a linear transformation. I'm going to leave that to you to verify. And just like we discussed yesterday, because any number defines a unique transformation this way, that is indeed a linear isomorphism. Okay? Now the problem here is perhaps the choice of where you're evaluating. Because there is nothing special about the number 1, really. You could have taken a linear transformation and evaluated at 2, whatever. In fact, you could have used whatever number whatsoever except the value at 0. Because if you were to take a linear transformation, evaluate that linear transformation at 0, it's going to give you back 0. That's not going to be an isomorphism. Any other input value is going to give you an isomorphism. You see, that's why, at least in abstract, it becomes important to think of this space as one thing, this space as another thing, that are isomorphic, they're basically the same, except that the way they are isomorphic is not unique. There's a choice involved. Okay? Okay. Now, the other way of seeing that these are isomorphic is going to involve the notion of dimension. Okay? At least for finite dimensional vector spaces, we're going to discuss what that means in a second. It turns out that there's a classification theorem. It says that any two finite dimensional vector spaces are isomorphic if and only if their dimension is the same. So this one non-negative integer completely classifies. It's a complete invariant of finite dimensional vector spaces. Okay? So I'll discuss that later. Okay, so let's talk about linear independence and span. How many of you have seen these notions before? Kind of remember? Okay. It was painful. Do you remember that as well? Okay, when I first learned this stuff, even what is the difference between linear independence and span? Even that is kind of confusing as far as I'm concerned. But hopefully, eventually, things are going to start making sense. Now, the way I think about linear independence is like this. So I have a vector space, and I have a set of vectors. I'm thinking of these as velocities, okay? I'm imagining that I have a robot, and V, this capital V, is my position space. And S, the collection of vectors that I chose, these are the admissible motions that I allow my robot to abide by, okay? Linear independence is about the non-redundancy of the different directions. Span is about where the robot can go, okay? So maybe in a second we can do some examples, but let me give the definitions. I take a subset. It doesn't need to be finite, arbitrary subset. We're going to call S linearly independent if for any finitely many distinct vectors, S1, S2, all the way up to Sn, if I were to take a linear combination of them, this is what is called the linear combination of them, of vectors. So these Ci's are numbers. I'm using them to scalar multiply or scale each of these vectors, and then I add all of them up. If this linear combination ends up being the 0 vector, so somehow you move a certain way, you move along S1 for C1 units, along S2 and C2 units, whatever, ultimately you say, oh, I ended up at 0. I ended up where I started with, where I started at. Whenever this happens, all of these coefficients have to be 0. That is to say, S is linearly independent if, given any finitely many directions included in it, if you do a loop around and end up where you started at, that means that actually you didn't move at all. Okay? This is like a robotics way of thinking about it, but I find it rather useful. Span, on the other hand, is, so span of S is the smallest vector subspace of V containing S. So what does that mean? What is the smallest vector space? Well, V itself is a vector space that contains S by definition, but maybe there are smaller vector spaces, vector subspaces of V. Okay, that means that you look at the collection of all vector spaces, vector subspaces of V that contains S, you take the intersection of them, and it turns out, we're not going to spend time on this, but it turns out that the intersection of vector subspaces is also a vector subspace. So you take the intersection of all of them, and that gives you this span. Okay? Any questions about these things? So maybe, let me give an example. Let's say that V is R3, three-dimensional space. Let's say that S is 1, 0, 0. Is this linearly independent? Well, yes. This is kind of a bizarre thing to say, but this is saying that if you're moving, so let's say I, so C times 1, 0, 0. So you're saying I have some magnitude C such that if I move in the x direction by C units, somehow I ended up at the origin. Well, certainly that means that you didn't move at all, right? C has to be 0. And what is the span of S? It's all those places that you can go. If you're only allowed to move in the x direction, that means that you can go in the negative direction too, but in one sort of vector space. That means that that is the whole x-axis. Okay? Of course, this is the simple situation. And in 2270, you learn how to sort of handle these and how to do algebra with these notations and how to sort of store all of these ideas into matrices and stuff like that. Let's not spend that much time on these things. Okay. So now that we have these two notions, I can define the notion of a basis. I'm going to do things slightly differently here, though, because there's a subtle technicality. I would like to imagine a basis of a vector space, something like the standard basis, whatever, to be not just an arbitrary set. An arbitrary set of vectors doesn't have any ordering associated to it. But when I'm thinking about the so-called standard basis of three-dimensional space, I'm not thinking about x, z, y axes, right? I'm thinking about x, y, z. That's always what I think. So that's the standard order. So it comes with an order. So I need to take that into account. So let V be a vector space formally. How can I handle these ordered vectors? Well, it's a tuple of vectors. But from the get-go, I don't know how many I need, how many vectors I need. So I'm going to say something like this. A tuple, which I'm going to denote by beta, so it's a tuple of vectors. V to the n is this Cartesian product, Cartesian power of V by itself. I'm taking n vectors in this order. Is a basis of V if, while the set containing all of these beta i's is both linearly independent, so there is no redundant vectors, no redundant directions, and you can go everywhere using these vectors. If for S now curly braces, recall, means that it's a set. That means that this is an unordered tuple. Because this is supposed to be somewhat of a formal math class, I think it's a good idea to make this distinction. So this is a subset of vectors. S is both linearly independent and it spans everything. Okay. Now going forward, I'm not going to distinguish beta and S. I'm just going to say beta is linearly independent and span of beta is V. But for this formal definition, I thought I think it's a good idea to distinguish. So here's an example. The so-called standard basis for, let's say, R4, four-dimensional space. Standard space. Then standard basis. It's denoted by sigma. So it's going to be sigma 1, sigma 2, sigma 3, sigma 4, ordered, where sigma 1 is 1, 0, 0, 0, sigma 2 is 0, 1, 0, 0, and so on. Okay, that's a standard basis. The point here is that if I were to look at the basis that starts with sigma 2, then sigma 1, and so on, that would not be the same basis. Okay, that would be a different basis. How about, let's say, the space of 2 by 3 matrices? What is the basis for that vector space? Any guesses?
Is it just like each has like just one, and each like part of the array and then zeros in the other spot?
Right, so how would you sort of think about, like, how would you guess that?
Like two vectors, which like one's a 1 by 3 and the other's a 1 by 3, and then like make up each matrix.
Well, I mean, the way I would imagine this is like this, right? So if I have a 2 by 3 matrix, that means that any matrix stores 6 numbers, right? They're supposed to be somewhat independent. And so I can just split each of these entries in such a way that each matrix contains only one non-zero entry. That's kind of my idea. And so indeed, the standard basis in this situation would look like something like this. E11, E11, E12, E13, and then E21, E22, E23, where Eij is that matrix that has a 1 in the ijth entry and 0 otherwise. Okay, that's a mouthful. Let's write it down. So first row, second column, 1, otherwise it's 0. Okay. Are we happy with the statement that any matrix, any 2 by 3 matrix, is a linear combination of these 6 matrices? Okay. How about linear independence? Well, if I were to take a linear combination of these, that would give me a matrix. Saying that that linear combination is 0 means that that matrix is a 0 matrix. And how do you get a 0 matrix? A 0 matrix is by definition that matrix, each of whose entries are 0. Okay? If this is not clear to you, I highly recommend you sort of sit down, think about the definitions, and go through the calculation. Any questions about this example? This is a very important example.
I mean, we've established that ordering matters. How do you order this?
Yeah.
It's a more complex
Yeah.
structure. Do you have a matrix of matrices?
Yeah, probably this way. Yeah. Yeah. That is true. Yeah, I mean, so this is one of the sort of main trends that's going to keep popping up in this class. I'm going to sort of pretend that things matter when I'm defining things, and I'm going to act like they don't matter, okay? And so you're going to have to come to terms with this. That's life. Another important thing here is that these matrices, perhaps you remember, are what are called rank 1 matrices too. And these particular matrices can be written as outer products of matrices, of vectors. This is not something that people discuss too much in 2270, but just to give an idea, and I want to keep writing this here, so I'm going to rewrite some of these. Somehow, these matrices are intimately related to the standard bases of R3 and R2. From 2270, I hope you would expect that ultimately this space of 2 by 3 matrices should be basically modulo some abstract math stuff, the same thing as the space of linear transformations from R3 to R2. So these are all machines that take as inputs 3-dimensional vectors, turn them into 2-dimensional vectors, assuming that you're left multiplying using these. You could have chosen to right multiply as well, but that's not what people typically do. So I'm going to rewrite these here. So E21, E22, E23. So another complication in this class compared to 3210 is also going to be index management too. Because matrices, when you have matrices, you have a bunch of indices. Now this is a 2 by 3 matrix. But I can write it as a product of a 2 by 1 matrix, so a row matrix, and a column, sorry, and a 1 by 3 matrix. Right, so I'm going to split this as 2 by 1 and then 1 by 3. How many of you remember matrix multiplication rules and stuff? Right, so the dimensions have to match and all that. Okay, this is how I remember. You put here, let me write it here perhaps. For matrix algebra stuff, if you're trying to multiply matrices, N, M, P, so if A is an M by M matrix, then B is an M by P matrix, then the product is well defined and it is supposed to be an M by P matrix, so the middle dimension drops. Okay. But note that this is 1, 0 multiplied by 1, 0, 0. So somehow E11 this is what is called the outer product. So you're multiplying two vectors, but you're not getting back a number. That would be something like an inner product, in this case it is not quite defined because these are not compatible in that direction. But in the other direction, because one of them is a column vector and the other one is a row vector, you can multiply them this way. Okay? When you take the outer product, you get this guy. And this is the first element in the standard basis in R2. This is the first element in the standard basis of R3. And so for instance, how can I split this again, the second one, similarly?
1, 0, and then 0, 1, 0.
Okay, so that's the pattern. Okay? Does this make sense? Okay? Any questions about this? In a second, I'm going to do this in abstract, and it's going to look more scary. Okay. So here's our first statement that we're going to prove. If I have a, oh wait, not mixed orders, this, Okay, yeah, let's prove this. That's fine. If I have a vector space with a basis like this, there are certain issues here, but let's fast forward that part. What I want to say is something like this. If I fix a finite basis like this in my vectors for my vector space, then any vector in that vector space has a unique decomposition as a linear combination of those basis vectors. So claim then for any v in V, there are unique numbers C1 to Cn. In other words, there's a unique n tuple of real numbers for any, recall this was my notation for, for any, for all. It's one of those logical quantifiers. For any v in V, there is, and here's a new symbol. If I put an exclam next to there exists, that means there's a unique. Okay, there's a unique tuple of real numbers such that V is Ci beta I, the sum of all of these. Okay, so this really has two things. One says you can represent any vector as a linear combination of these basis vectors. That's about the span part. The uniqueness part is about the non-redundancy. You get to have a unique representation. That's the first part. Second part, more sort of highbrow way of saying the same thing, actually. M sub beta going from V to the space of matrices of dimension n by 1, so column matrices, defined by sending V to C1, C2, Cn, where Ci are defined in the first part. This. This is a linear isomorphism. It's an isomorphism of vector spaces. The second part is precisely what you use when in 2270, for instance, you think of vectors, any sort of vector pretty much, as a column matrix. Okay? The point here is that it depends on the basis that you chose. And so this M sub beta of V is called the matrix representative of the vector V. of v relative to beta. Okay. I should also mention that whenever I underline a phrase, that means that I am defining that phrase. Okay, let's do the proof first, and then maybe we can sort of we can talk about how to interpret this. I have a certain stunt in my mind. I don't know if it's going to work, but we're going to see. Okay, so we're going to do a proof now. I should mention, many of the things that we're doing this week, they are more of an algebraic flavor, like they have a more algebraic flavor. Starting from next week, things are going to get more calculus-like, let's say. We're going to start taking epsilons and deltas. Maybe not next week, but certainly the week after. I like always to handle the algebra part first and get rid of it and put it in the toolbox. Okay, so we have two parts. And we have, I hope you remember from 3210, a bunch of different ways of proving things. So let's start with item 1. I fix a v. At least for this proof, let me be slightly formal, write things down explicitly, more sort of, without, abbreviating things and so on. As time goes by, I'm going to sort of write less and less of the proofs. Fix a vector. By the definition of beta being a basis, I know that the span of beta equals capital V. Have okay. In particular, lowercase v, this vector that I chose, that was arbitrary, but still, is in the span of beta. By definition, that means, if you think about it, perhaps, that means that I can indeed write v as a linear combination of vectors in beta. Any issues with this or comments?
We're not showing it's unique.
Yes, I didn't say I finished, but at least they exist. Fair enough. Now, how do we show that these numbers, in fact, in this order, are unique? Any guesses? How do you show that something is unique?
Assume that it's not unique and then prove that, assume that there's two of them and then prove that they're equal.
Exactly. So you're saying, okay, so let's say that somehow I'm given some other sort of numbers that are named differently. Ultimately, they have to be the same numbers. So let's say there's d1, d2, all the way up to dn in R, such that B equals the linear combination of beta i's using these new numbers, possibly new numbers. Well, if that is the case, then 0, the 0 vector is v minus v, which means that 0 equals this sum minus this sum. these are finite sums, I can collect the corresponding terms. And now, this is yet another linear combination of beta i's that happen to equal to 0. But then again, by the definition of a basis, I know that the vectors included in the basis are linearly independent, which means that these coefficients all have to be 0. Beta i's are linearly independent. By definition, that means that for any I, Ci minus Di equals 0. In other words, for any I, Ci has to be equal to Di. And so these supposedly new numbers that give me the same vector actually are not not new numbers. They were the old numbers that I already had. So that's the uniqueness. Existence, uniqueness. That's the end of the proof of item 1. Okay? Any comments or questions about this? Now, why did I say that sort of the flavor of proofs are kind of different in linear algebra? Well, in a sense, we're just writing the definitions out and like reordering the things or rewriting them and stuff like that. But probably from 3210, you remember, when it comes to calculus and analysis, there's a bunch of estimations and some sort of more painful things, right? But we're going to get to that later. Another thing perhaps is, how did I come up with these even names? How did I come up with C1, C2, and so on? Or D? Why didn't I use some other letter? The point is that that's a matter of sort of choice. I like using C for constant, and then if these are the first constants, the next constant should be perhaps the next letter. This is something that you sort of get accustomed to as you keep writing more and more sort of formal proofs. Of course, ultimately the numbers, so the names of these letters actually don't matter, right? So these are still dummy variables at the end of the day. But still, when you're first getting used to writing proofs, even figuring out what to call that thing that you're going to use as a dummy variable, it's going to sort of take some time, I'm expecting. But eventually, you learn how to handle these things. Are we all fine with the first part? Okay, how about the second part? So now I have this function that takes as an input vector v. So I'm imagining this v to be sort of reality, okay? And so this m sub beta tells me a bunch of numbers. It's something like a map. Gives me the coordinate system, or gives me the chart. Okay, so I don't have space, so I'm going to have to delete that part. At the very least, let's delete this part. By the first part, I know that the forward direction is a well-defined function. Given any vector, there are unique numbers that I know come up like this. So this is well-defined. Right? So because if I take v, the first part tells me this tuple of numbers. I say, okay, so take these and turn this into, or store this tuple in a matrix, and in this order. This is well-defined. And again, taking a vector like this, or taking a matrix like this, and turning it into a linear combination like this, really tells me that this is a function that has a functional inverse. And then by the exercise that I gave, I think, yesterday, all I need to show then is that m sub beta is a linear transformation. Automatically, its inverse too is going to be a linear transformation. M sub beta is well defined. And has a functional inverse. By the previous exercise from yesterday, I think, it suffices to show that m sub beta is a linear transformation. It suffices to show is linear. Okay, now we need to do two things. I can actually turn it into one, but let's not lump things together. We need to show that m sub beta respects vector addition and scalar multiplication. I'm going to leave scalar multiplication part to you. It's slightly easier, I think. You're going to get the idea when I do the vector addition part. Okay, this I'm leaving to you. Of course, when I write it like this, you should really think about what is actually happening here, right? So here I have this V, it's this abstract vector space. I don't know what is happening, and these are like axiomatically defined. But there's a scalar multiplication, and this makes perfect sense. Then I apply m sub beta, look at its matrix representation. I want that matrix representation to be the same thing as the C scalar multiple of the matrix representation of V, of course, relative to the same basis. Okay, that I'm going to leave to you. I want to show that for any V1 and V2 and V, maybe I should say want, the matrix representative of the sum of the two vectors, I want this matrix to be the sum of the matrix representative of V1 plus sum of that and the matrix representative of V2. Plus. And again, while I'm not explicitly saying this, this plus is matrix addition. This plus is this abstract addition I don't know anything about. This is what I want. Okay. I need some more space, I think, but let's go on here. Hopefully I'll be able to finish it today. So by the first part, I know that I can write V1 as, let's say, C1I beta I, and V2 as the sum of C2I beta I's. Okay? I use the first part. So this is what I wanted. Let me continue over there. Now, we need to sort of rewrite things a bunch of times, and hopefully things are going to sort of cancel out and stuff. So how do you show this equality? You start from one side, do a bunch of things, get back the one on the other side. Okay. I'm going to stop writing the indices and summations at some point because it becomes cumbersome. This is still vector addition in V, but I can still combine these. Okay, but I know where m sub beta takes this particular vector to. C1, 1 plus C2, 1, all the way up to C1n plus C2n. Oh, but I know how to split this column matrix as the sum of two column matrices. But of course, this first one, I split this in such a way that what I wanted pops out. I know that this is the matrix representative of B1, and I know that this is the matrix representative of V2. That's how the cookie crumbles. Okay, and just move things around. As you can imagine, I'm not that much of an algebra person. Of course, you need to know some algebra, but I like calculus a little bit more, for better or worse, for you. But this is what you do. Okay. Any comments or questions? Okay. This stunt I mentioned, I think we're going to do on Friday. But the point of splitting the vector spaces V and column, or the spaces of column vectors, or column matrices, is because we have a bunch of, in this class, vector spaces where this matrix representatives don't quite work as well. Spaces of continuous functions, whatever. So to handle those, you really need to think about vector spaces without bases, or you need to be able to do that. Okay, thank you. I'll see you on Friday. Okay, let's start. Good morning. So problem set 1 is up on Canvas. If you go to Canvas, under the assignments tab, under problem set 1, now there's a PDF file, so it looks like this. Like I said before, the sort of colored text is, these are links that you, if you so choose, you can follow and sort of learn a little bit more about some of the objects that you're going to be interacting with. These are not necessary. It's sort of like the lore, if you want, or flavor text. So don't mistake it. For instance, in problem 5, there's a certain equation, matrix equation, that is highlighted. If you click on that, it takes you to the web page, Wikipedia page for a theorem called the Cayley-Hamilton theorem. Just because I link it like this doesn't mean that you need to know what that means. The point here is that using simple methods, you should still be able to prove or disprove the statement. The idea perhaps is that this equation is not coming from, coming out of nowhere. It's something important. Okay. So I want to say a couple words about problem sets and how you should sort of approach to problem sets, which is basically going to be the main thing in this class, really. It's like you do math, you learn math by doing math somehow. And so you're going to be spending most of your time throughout the semester, working on these problems. So I want to sort of discuss a little bit. And then on Monday, I would like to discuss more how to approach statements in this class. Those of you who've taken the previous class from me, they're familiar with this idea, and you're going to see in the problem set as well, because both in the problem sets and in the exams, I'm not going to tell you prove this or that. I'm going to be neutral. It's going to be your job to figure out, first of all, if the statement is correct to begin with. So I'm going to try to trick you, perhaps. And then you're going to realize that if someone tells you that something is correct, it's significantly easier to prove it than to first figuring out and then proving or disproving it. Part of it is because this is all about developing mathematical maturity, and when it comes to sort of, let's say, the applications of sort of learning proof-based math, is that you learn how to become a little bit more skeptical. So when people tell you things, it should be in your power to believe or not believe it. And pure math is one of those topics where you can question everything, right? You can keep asking why and why and why, and ultimately it keeps going. Of course, it becomes impractical at some point to keep questioning things because you only have so much time, but still. So regarding the design, I guess that's sort of what I wanted to say. So the statements are always neutral, and you're going to read this as well. I wrote this in the specification document also. And so how do I come up with problems? Well, some of these problems actually are, I took directly from my problem sets when I taught 2270 1 year ago. Some of these are from the textbook. Typically what I do is I take snapshots of the problems in the textbook. I feed them to one LLM, generates the code for me. So I scrape all the problems, and then I sort of adjust and I tweak the problems and so on. I restate them and so on. And the ones I like, I put in the problem set. The other ones I sort of leave alone. That's basically the idea. And so we were perhaps talking about sort of buying the textbook. If the only reason you're going to buy the textbook is so that you have access to the problems, then probably that's not a good way to use your hard-earned cash, because the problems are going to be self-contained. You pay to get this class, and in the class everything is here. Okay. So each week the problem sets themselves are going to contain the problems that you're going to need to solve. That's that. AI stuff. Basically, you can use them, but I don't want you to sort of just take the PDF file, plug it into your favorite LLM, and have it print out the solutions. But you can discuss what you're trying to do and so on. I'm going to ask you to list the URLs of your interactions. For instance, if you're using ChatGPT, it generates the URL for your chat and so on. There's a bunch of different options for you to do this. That's that. Another thing here is that there's a section called How to Submit. It's a two-step process. This is what I've been using ever since I started teaching here. So the first step is I'm going to ask you to fill out a certain Google form, whose link is here. I'm going to ask you things about the problem itself, or the problem set itself. How long did it take you to do the problems and so on? And if there are other questions that I'm wondering about, I'm going to ask those as well. So for instance, in the Google form for the first problem set, I'm going to ask things like, oh, how many proof-based math classes have you taken? Okay. This is so that I have an idea as to who I'm working with. The second step is going to be, well, you upload your work on Gradescope. Okay, this is the first step, this is the second step. These are not optional. I'm going to ask you to fill out the form every single time, and you're going to get a 0 if you don't fill it out, okay? So that's that. And when is it due? It's due next Friday, so August 29 at 11:59 p.m. Mountain Time. So that's that. So regarding how you should approach working on the problem sets, is that the way I imagine this is, so this whole class is of a cyclical nature. Okay, so today is a Friday, and Saturday, Sunday, Monday, Tuesday, Wednesday, Thursday, and then Friday next week. Okay, it will always be the case that starting from next Friday, you have a boss. You have something to do, you have something, either an exam or a problem set that Friday. And so I would suggest that you start working on, at least for problem sets, the Friday it is uploaded. So I suggest that you start working on problem set 1 today. It doesn't need to be like super serious, but at the very least, for half an hour, you should have a look at every single problem, have an idea, and so on. I am a big believer in sort of in the subconscious, and you sort of have a look at the problem. Maybe you have no idea, but it's in the back of your head, and like you sleep on it and stuff like that, and all that. The point here is that even though I said in the first day the weekly workload is 8 to 12 hours, somehow there's a difference between, well, working 10 hours one day as opposed to working 2 hours 5 days. Next week we're going to see how to actually distinguish these two from a mathematical point of view. It turns out that these are sort of different norms. So you want to keep the L infinity norm small somehow. So you don't want sort of like spikes in the graph of how much you're working, right? So this is each day, and like you don't want your workload to be like this. This is not good. You're not going to internalize things. You don't want spikes. You want something like this. You want just a little bit every day. Maybe like this. This is better. It's going to turn out that this is controlled by the so-called L infinity norm. This is more like, so the area underneath is the total work that you end up doing. That's more like the L1 norm we're going to see. Okay, so that's that. Is there anything else I want to say? Maybe I should say also this, that I'm still thinking about how to handle the AI situation a little bit, because yesterday I did some experiments with DeepSeek. If you were to take this problem set, the PDF, and put it into DeepSeek, one of these AI systems, in about 36 seconds, it generates pretty much complete solutions. Okay, I'm telling you, not so that you do it, but I'm doing it. So maybe what we'll do is something like this. So the solutions are not complete, 100% complete. So maybe I'll do something like this. Each week I'll try 1 or 2 AI systems and sort of like have them generate the solutions and then annotate the solutions, put commentary on them, and sort of turn them into sort of teaching materials. I'm thinking of something like that, but we'll see. Any questions about any of this? Perhaps I should also mention that, so in the first problem set, there are 5 problems. You're going to see each of these problems have multiple parts. They're rather long, and the problem sets are designed so that it takes the whole week for you to finish, okay? So it's not a problem. It's perfectly normal if you look at a problem and you're sort of like confused or whatever. These are designed so that you keep going back at it, and by the end of perhaps 1 week, you're sort of 90% there. 90% completion, at 90% completion. And right after this class, I'm gonna have a meeting with our grader, who I know personally. He's taken classes from me before and so on. And he's graded for me as well. So what's gonna happen is that probably 5%, so 5 points out of 10 points is gonna be basically from completion. And then I'm gonna choose probably one problem that's gonna be random, or somewhat random. At least you're not gonna know which problem it's gonna be. I'm gonna grade it by myself. That's gonna be for accuracy, okay? And this time, we're gonna pay special attention to detecting unauthorized AI use. So in the form, for instance, there's gonna be a part where you disclose where you used your AI, or where you used AI, in which way, and so on, where you sort of list the URLs or whatever. So we're gonna sort of cross-reference, and we're gonna make sure that people are not sort of using AI without awareness, let's say, okay? Okay, so that's that. That's all I wanted to say about problem sets. Okay. So the way this is going to work is, the only way this can work, perhaps, is that even though the problems looks scary at first, you need to have a certain amount of trust in me that I actually know what I'm doing, and you can actually solve these problems, okay? There's nothing crazy going on, really. Okay. So that's that. So I want to start with an exercise. Remember, on Wednesday, we talked about the space of, as an example, this space of 2 by 3 matrices, and we came up with a certain basis for it. And I mentioned then that, maybe later on we're going to do the same thing, but in abstract. So here, this exercise is this abstract version of the same idea. And it goes like this. Somehow, if you have 2 vector spaces, where each of the vector spaces has a specified basis, then it turns out that there's a natural basis for the space of linear transformations between them. Okay, so this exercise is about that. And let V and W be vector spaces. Beta ordered tuple. Let's say that beta is a basis for V, and let's say gamma is a basis for W. Basis for V, gamma, be a basis for W. Just need to look at my notes because the indexing gets complicated here. Okay. For any j that varies between 1 and n, and for any I that varies between 1 and m, define Lij. So for any ij pair, I want to define a certain linear transformation from V to W. That's going to be of a specific form, namely by for any k Lij beta k equals gamma I if j equals k, 0 otherwise. So this is the perhaps benefit of looking at linear transformations and bases, because of this unique linear combination property of bases, you can define a linear transformation simply by describing what it does to basis elements. Okay? The claim is the collection of all Lij's then constitutes a basis for the linear transformations from V to W. Yes, and then L to 1 all the way up to L to n, and then dot 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 L m1 all the way up to L mn. So this, there are n times m many linear transformations here. This is a basis for this. Once you sort of open everything up, you're going to realize that this is nothing but sort of this outer product of matrices, of vectors or column matrices in abstract, let's say. Okay, so that's that. Here's an example. I still want to say a couple more words about this notion of a basis. And then we're going to be able to define notions of dimension and sort of state this classification theorem and so on. But look at this example. R bracket x. How many of you have seen this notation before? Okay, one person. So what is this?
This is the set of real value, I guess polynomials with real coefficients.
Yeah, with one variable, exactly.
Yeah, and this works as a vector space, it works as a ring, it works as a bunch of things.
Yes, yes, it works in many ways, but for now I want to think of it as a vector space, because if I have two polynomials, certainly I can add them up. That's still a polynomial. And if I have a polynomial, I can scalar multiply that polynomial by any number whatsoever, and that would still be a polynomial. So this is the vector space of polynomials with one variable, x, and real coefficients. Now, the way we defined the notion of a basis required that I had finitely many vectors in my vector space. Now, in this case, that doesn't quite work. But in a sense, if I'm allowed infinitely many vectors, I still have an infinite tuple of vectors that are linearly independent and that span everything. So then any p, any polynomial, is a linear combination, is a combination, and uniquely so, of Well, monomials. 1x, x squared, x cubed, and so on, all the way up to infinity. Okay. So this is why people would call this a basis as well, even though it's not finitely many. In this class, whenever we talk about the basis, it's going to be a finite basis, but technically this is also a basis. Okay, so we're going to call this a Hamel basis. Hamel was a mathematician, as I know. This is where things get a little bit abstract, because for instance, then you can imagine something like the space of all formal power series. Not going to write that down, but you can imagine, well, in 3210, you saw sort of this idea of, okay, so I can write a formal power series, and I can ask whether or not it converges or not, right? Without looking at a power series or without verifying a power series converges, you can still talk about it as a mathematical object. And you can put all such formal power series into a set. Turns out, again, it's a vector space. But then you won't be able to find a bunch of vectors in that space such that any formal power series whatsoever can be written as a finite linear combination. Whenever you say linear combination, that means it's a finite linear combination. But this is an axiom somehow that any vector space whatsoever, no matter how abstract, has a Hamel basis. It's a crazy thing to say, and this is part of this abstract, super abstract math. So imagine the space of all continuous functions. Somehow there's a basis for it, which means that any continuous function can be written as a finite linear combination of a bunch of vectors in that specified set you chose. As far as I'm concerned, this is not very applicable, and it's not going to be of use for us in this class, but I thought it would be a good idea to mention this at the very least. And I also should mention that if someone claims that they're proving this, they are not actually. Okay, there's another axiom that is equivalent to this, which is this axiom of choice or whatever. We're not going to be worried about these kind of things. What is more important is the classification theorem. This is going to be important. And this is the basis of, no pun intended, this is the basis of perhaps dimensional analysis. Now, for instance, if you're doing physics or if you're trying to solve a differential equation, whatever, you would want the quantities to have the same units, right? It turns out that you can do a similar thing even in this abstract situation. Because this classification theorem tells you whether or not, given two nice vector spaces, let's say, whether or not they are isomorphic as vector spaces. It has two parts. Oh, let me write it this way. Did I write it here? Yeah. part one. Let V be a vector space if beta is a basis of V, then for any other basis, vector spaces have many bases. Then for any basis gamma, let's say it's an M tuple. In fact, N and M has to be the same number. So there are many bases, but somehow if you can write any vector whatsoever in your vector space as a unique linear combination of n vectors, then for any basis, that basis has to contain exactly n vectors. And so this common number is defined to be the dimension of V. Okay? So for instance, you cannot span R2 using one vector. It's impossible. Okay? You can span R2 using three vectors, but they cannot be linearly independent. There has to be some redundancy there. Okay? So this common number is called a dimension. And in this case, V is called finite dimensional. This common non-negative integer, it could be 0, technically. Integer, so this is the dimension of V and is denoted by dim of V. If you want to be more specific, you would want to call this linear dimension, because it turns out that there are many other different notions of dimension, which we're not going to worry too much about in this class. Second part of the classification says that if you have two finite dimensional vector spaces, they are isomorphic as vector spaces if and only if they have the same dimension. So this non-negative integer that you associate to each vector space, insofar as they are finite dimensional, completely classifies their isomorphism class. Finite dimensional vector spaces, then V is isomorphic to W if and only if dim of V equals dim of W. Any comments or questions about this? So looking back, we had this exercise from this past Tuesday. like this. And initially, the way we handled this was by saying, oh, from this space, I can write a linear transformation that goes to this. That is an invertible linear transformation. Well, what you can do is you can realize that this is one-dimensional. This too is one-dimensional, so that these two are finite-dimensional vector spaces. By the classification theorem, they have to be isomorphic. So this gives you some amount of flexibility. And in fact, now that I've told you this should be also fine. The space of linear transformations from Rn to Rm is isomorphic to R to the Nm. So for instance, a linear transformation from R2 to R2 is specified using 4 numbers. If you think a little bit more about this, if you formalize this idea, that really means that the space of linear transformations from R2 to R2 is 4-dimensional, which means that that has to be isomorphic. That space has to be isomorphic as a vector space to R4. Okay? So that's how you handle these things. And so if you're trying to sort of do certain things, it becomes very important to be able to count the dimension of the space that you're using to figure out if things match. That's what I mean when I mentioned this dimensional analysis business. Because somehow vector spaces are spaces. These are complicated things to think about. But insofar as they are finite dimensional, at the very least, the first thing you should look at is the dimension. When they give you a vector space, immediately compute, I would suggest, the dimension of it. This is not always going to help us out in every single situation in this class, because many of the vector spaces that we're going to be looking at are infinite dimensional, in which case this doesn't say anything. So the space of continuous functions. It's infinite dimensional, but how infinite, right? You don't want to go there. You don't want to start talking about, I mean, in my humble opinion, you shouldn't go there. When it gets to infinities, things get more complicated. Try to stay away. At least that's what I do.
Question?
Yes.
So you're saying that if two vector spaces have the same dimension, it's always possible to find some invertible linear transformation between
Yes.
the spaces?
Yes.
Yeah.
Yeah, I mean, let's have a look. Okay, so maybe I'll say a couple words about how to prove this. But before going into that, there is an even more important theorem, again coming from 2270, which is this rank-nullity theorem, or in other words, the so-called fundamental theorem of linear algebra. So I want to state that as well. Once I state it, if we have time today, maybe we can sort of discuss a little bit how to sort of handle these things. So if I have a linear transformation between two vector spaces, to that linear transformation too, I can associate two numbers by way of using dimensions. One of them is the dimension of the kernel. That is called the nullity of the transformation. And the other one is the dimension of the image. That is called the rank of the linear transformation. So definition. This into 2. And L be a linear transformation from V to W. The nullity of L is a dimension of its kernel, possibly infinite. And the rank of L is a dimension of the image, again, possibly infinite. The nullity and rank of L are defined by this. So dimension of the kernel. This is a non-negative integer, or perhaps something larger than that. So this is my notation for that subset of the integers, z, but then this is less than, greater than or equal to 0 as a subscript means that I don't allow negative numbers, or infinity. Of course, this notion, as far as I'm concerned, is useful insofar as this nullity is a finite number, but there are situations where it is infinite also. And then the rank is the dimension of the image. The fundamental theorem of linear algebra says that if you have a linear transformation defined on a finite dimensional vector space, you don't actually need to assume this, but for simplicity, let's say it like that. In fact, you can go even further. You can say, let's have a linear transformation between finite dimensional vector spaces. Then it turns out that the dimension of the input space equals rank plus nullity of the transformation. Let V and W be finite dimensional vector spaces, and L be a linear transformation from V to W. Then the dimension of the input space, so dim of V equals nullity of L plus rank of L. How many of you remember something like this from 2270? In 2270, typically what you do is you learn something called Gaussian elimination. Right? So you take your matrix and then you row reduce it and stuff like that, and you look at the pivot columns. So the number of pivot columns is supposed to be the rank. It's the same rank, it turns out. And the rest is the null space, right? The rest goes to the null space. So the dimension of B in terms of matrices is the number of columns in your transformation. Number of columns is the number of pivot columns plus the number of vectors in the, or columns in the null space. That's sort of like a matrix way of thinking about it. This is the more abstract way of thinking about it. Okay, we have about like 6-7 minutes. So let's try to discuss a little bit how to tackle these problems. I'm not going to prove these, but maybe I can mention just a little bit. Here. There are sort of additions to this statement, by the way. If you've taken linear 2270, you also look at, for instance, the nullity of L transpose. It's not clear what that transpose means in this abstract setting, but you can still make sense of it. And you have some statements about the orthogonality of certain spaces and stuff like that. We, again, in this generality, have no idea what orthogonal means. We're going to actually start discussing orthogonality next week. So far, you cannot actually mention this. Well, you can, but it looks even more abstract. So we're not going to do it. So for the classification, for the first part, well, let's take beta and gamma, okay? Say both of them are bases. But say m is greater than n, okay? So this is my notation for saying that m is a strictly greater than number than n. So this is one of those proof methods. What I want to do here is to come up with a contradiction, okay? What should be the case is that there are two ways to go about doing this. One way of saying, so using either the spanning idea or the linear independence idea, let's say you want to do the linear independence. You have n vectors coming from beta that are linearly independent. For each vector in gamma, because beta is a basis, you should be able to write any element here as a linear combination of vectors here. Now argue that in fact the vectors included in gamma